All right, so we are going to be jumping into the next topic after percent composition, which is going to focus solely on hydrates. We talked a little bit about this in the last one, but now we're going to take a little bit more time to get into hydrates, which will be applied to in a lab. So a hydrate, which we talked about before, has ions which are attached to one or more water molecules, and it's a very specific ratio. So for every one sodium carbonate compound we have 10 water molecules attached to them. And it's built right into the formula. Just remember this dot represents a hydrate, but don't think about it as a multiplication symbol. Think about it as an addition symbol. Now, one term that we haven't talked about before is an anhydrous salt. So if I have Na2CO3 with my 10 water molecules, this entire formula is going to represent the hydrate. However, when we actually can remove the water through heating from the hydrate, we're left with just the salt. And this is what the anhydrous salt would be. It's just the hydrate without the water molecule. So in our case, sodium carbonate. So you're going to see me when we get into the experimental data looking at this formula quite a bit. This would be our hydrate. It then gets heated. And then this is the anhydrous salt without the water. And then this water is what evaporates out. Okay, and that's going to be important. But let's first start with number 1 on here, which is just going to review what we did in percent composition by using the formula. So I am looking at my BaCl2 and I want to know the percent water by mass. So I'm going to start off first with my barium chloride. So I'm looking at this whole hydrate. So my barium mass off the periodic table is 137.33. I have my 2 chlorine, so 2 times 35.453. And then I'm going to add in my 2 water molecules. And remember, we added this up before. Water is always going to be 18.02. Okay, and I always do water as a group so that you don't mess up how many hydrogens and oxygens you have there. So when you type that in, it's 137.33 plus my 2 times 35.453 plus my 2 times 18.02, I get a mass there of 244.2, and I'm around this to the tenths, 8. Okay, so that is the mass of the entire hydrate. Okay, and then I'm going to be looking at the water, so I'm just going to be interested in these 2 waters. So when I come over here, I'm going to have my part, which is going to be the water, over the whole thing, which is going to be the hydrate times 100. So for the water, I'm going to have my 2 waters times 18.02 over the mass of the hydrate, which is 244.28 times 100. So when you plug that in, 18.02 divided by my 244.28, making sure I do the times 100, you're going to get 14.75%. Okay, so if I had 100 grams of this hydrate, 14.75 grams of it would be from the water. All right, let's look at what lab data we could see and questions how you go about solving those. So these ones, you're not going to be given a formula. You're going to be given data from a lab scenario. So this says I have 3 grams of a hydrated salt, and it's heated to a constant mass of 2.32. Constant mass here just means that as you heat it and water evaporates out, when you get a constant mass, there's no more water left to evaporate. Okay, all the water has been removed. So when we look at what these values mean, and we go back to this formula that I showed you up above, that we're going to have a hydrate that we heat, and we're going to have an anhydrous salt and water. The 3 grams is the hydrate. Okay, and then this 2.32, this is what's left in the crucible or in our container. That is going to be the anhydrous salt. And then water, we don't know. So that's going to be X. Okay, so when I go to solve for my water amount, which I'm going to need, because when we look at the percent composition, we need our water divided by my original hydrate times 100. Okay, water is just going to be the difference of these 2. So I'm going to have my 3 minus my 2.32 gives me 0.68 grams. Okay, that is going to be the actual amount that goes up here. So probably the biggest mistake is that students will just automatically throw the other number into the numerator, but you have to see if that's actually the water amount. So again, whenever you heat it and this is what's left over, that's always going to be the anhydrous salt, and then you got to figure out how much water evaporated out of it. So this will then be here 0.68 divided by 3 times 100, which would give me 22.67% water. All right, so let's do one more together. I'm going to have you try the last one out on your own. So this one, we have a substance that comes in hydrated form. If 5 grams of the sample is heated to a constant mass of 1.85 grams, what is the percent by water? So same thing, I'm going to first just kind of look at, well, what information do I have? I have to understand my hydrate, how much anhydrous salt was left, and then how much water evaporated out. So for the hydrate, I have a 5-gram sample. That's how much I started with. Okay, then what was heated to a constant mass was my 1.85 grams. So this was left in the container, which is usually a crucible or evaporating dish. And then I want to know how much of water evaporated out. So if I find X here, which is my water amount, I would simply just do 5 minus 1.85, which is 3.15 grams. So when I go to put this in for water over my hydrate times 100, I could plug in this 3.15. It's also acceptable up here to just write 5 minus the 1.85. You don't have to do it as a separate step over the original amount of 5. Okay, and then when we do that, we would have 3.15 divided by my original hydrate mass times 100, which would give us 63.00%. All right, so this would be a good spot to pause, see if you can test yourself out on this last one, and then come back and check to see how you did. All right, so for this one, it's a little bit different because the wording's a little bit different, but if you've been paying attention to what I've been saying, hopefully you were able to kind of plug in values here to figure out what information you needed. So I have a 4-gram sample of a hydrate, and it says it loses 0.793 grams of water. So in this case, it's actually giving you the water amount already. And really, those are the only 2 values that you would need. But let's just say you were interested in that. This would tell me that in my container, I should have had then 3.207 grams left in my container. But I'm just interested in how much water evaporated out and what was my original hydrate. Okay, so same thing, I'm going to be doing water, which is my part, over the whole hydrate times 100. So this would be 0.793 divided by 4.00 times 100, which rounding off to the hundredths place would give me 19.83%. Okay. All right, so now you're going to go do some practice. Definitely use your notes to help you figure out kind of the setup of these. And don't forget about how we're using GFMs when we're given the formula.